So the structure of this talk is I'm going to be talking about three things before I introduce David to present our solution to what you need to know. The three sections I'm going to be talking about is what is the problem with regular expressions? Second, why is it slow in Python? And third, what do we do about it? How can you identify what regular expressions will be slow in Python, and what solutions can you have to them, and kind of why they're slow? And then we'll finally go into a brief intro to Rust and using its algorithms to do this better. So I'm going to start immediately with a demo, because I think working code is often the easiest. And what we're going to do for this demo is we're going to use a regular expression that I've crafted that's kind of real world. Not perfect, but you know, hey, pretty good. So we're going to immediately pull it up, and this regular expression matches on a URL or an email address. You can kind of see it there, and like all regular expressions, joking aside, it's here. The first part is the, oh, did I cut out? I'll try to stay a little closer. The first part here is the URL, and the second part here is the email address. Now I'm compiling this regular expression twice. Once I'm doing it with the built-in regular expression, and the second time I'm doing it with our solution, which is a DFA engine. We'll talk about what that really means in a second. So now that I've got the regular expressions compiled, let's just show that they both work. Both implementations work here. Immediately we see that the email address is correctly parsed out. Hi, I work at CrowdStrike. And additionally, for Python and Ruhr. That's not really interesting. So let's import the Zen of Python and do that to get a big string. In this case, only 1,000. Now, let's take a quick timing. And my human brain can't interpret zeros very well, so we're going to times it by 10. Let's just go with twice. I don't feel like typing the second version, so let's just do that. Times it by 100. So immediately, we're now waiting, and waiting, and waiting. Ah, there we go. So Python took 6.3 seconds right now, and the Ruhr only took 0.4 seconds. Now, if you care about performance, this is huge. If you care, when you're dealing with regular expressions, and this seemingly decently crafted regular expression, it's not like this is cheating. This isn't one of those examples where I'm trying to show you that regular expressions are evil and then I've got the right solution. This is 10 times the difference in performance. When you're parsing large amounts of string data where you really care about the performance, you need to care about how the regular expression is working internally. So let's go back to my slides here. Now, in here, I'm basically saying this isn't Rust. I'm not here to tell you, and we're not here to tell you that Rust is the solution. It's not. It's algorithms. This is quicksort versus bubble sort. And this graph here is stolen as attributed at the bottom for what happens with these different regular expressions. Now, Ruhr is not on this list, but Python is. And you can immediately see we're in Python following exponential growth. The scale on the left is logarithmic. Whereas a correctly NFA version, NFA to DFA version, is going to be following this blue line, which we do see, and I just demonstrated. As you grow string length, Python gets exponentially worse if you're not careful with your regular expressions, whereas a correct DFA engine can do it in linear scaling with string length. So, back to part 2, right? We need to understand what's going on. Why is Python slow? Well, I think that a great way to understand how a tool is built is to have a little bit of its history in mind. Regular expressions were introduced in the 1950s in concept. Now, the final form that we would recognize today did not occur until the 1960s with Ken Thompson, who we can all thank for VI. And if you use Emacs, well, there's no helping you. So we see immediately, though, at these early roots in Unix and in VI, that regular expressions really had two purposes. One was within text editors, and the second was within programming languages. We're talking about lexers, basically. And from those roots, we ended up with the definition of deterministic finite automata, DFA, and its superset, non-deterministic finite automata. It turns out that all Perl regular expressions classify as NFA, non-deterministic. And if you take a subset of that, it becomes deterministic. You can take all of that subset and make it into a deterministic state machine. But there's this weird term that I can be using, and what's really going on in Python is when you take a naive implementation of an NFA graph, you'll end up, when you're executing the regular expression, with this concept called backtracking. Now, it's really easiest to see this in a diagram. And I really love this example, so I'm just stealing it because I think it's a perfect example. If we're taking a simple regular expression, AB, AB, or A, B, 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 we immediately see what's going on. When I convert that to just this diagram, which is a finite automata, we see that at the outset, we have a choice. And the computer can't make two choices simultaneously. This isn't a quantum computer. So what ends up happening is you have to guess. You have to go down one of these paths. So if we're talking about matching A, B, B, C, which won't match, the first time we go match the top graph, A, okay, so far so good, B, so far so good. Oh, another A, oh, shoot. Let's go back to the beginning. All right, second version, A, B, so far good. Another B, oh, this is awesome. Nope, back to the beginning, oh, I didn't match. You'll notice that the computer did a whole bunch of work reprocessing the same versions of the string at the same time. Now, if we're just making this a little bit more complicated, in this example, I've taken that same example, and what we're doing here is highlighting the difference between non-deterministic and deterministic automata. In deterministic automata, it's always guaranteed that from the current iteration of the string, you're going to derive to the next point, just from that one letter. So here, when we think about the same A, B, B, C, which isn't going to match, we only go through the string once. Now, the example I'm using for limited time includes the state from the non-deterministic version. But we see A, we consume, B, we consume. We immediately go down the B path. We know we don't need to think about this other path. We only had the one variable. And we immediately know we don't match. I'm using not matching because it is a worst case for most regular expressions. And this brings us to kind of like, okay, you showed me a demo. It's way faster. I get the DFAs are faster. And I've kind of given you a little bit of a clue about what an NFA structure is, and that really does underline what's internal to Python. So why don't we just fix Python? And the answer is the batteries are included. You're getting more features for having an NFA backtracking engine at your internals. This isn't new. This is like all programming languages, Java, C#, etc., Ruby. You get features like look ahead, look behind, back referencing, which is different than backtracking. Back referencing is the /number, where you're referencing a previously defined group. Conditional branching, which is, we're not going to talk about it. But you get the batteries. So what I want to do now is get to my third part before I turn it over to David, which is I want to help build a little bit of an intuition about when a regular expression would be slow in a backtracking engine. And I think Microsoft put this really well in their C# documentation on this topic. It's on you. It's on the developer. The regular expression is not something that you can just take from a user and blindly execute. It's a sharp tool when you've got a backtracking engine. So that's kind of why I like DFA engines, and it fits our use case really well, because we have a case where the input is not coming from a programmer. It's coming from somebody that doesn't care about performance. They care about our domain. So it's on you. That's why you need to have this intuition. And what you kind of come with is the example that I really love to show that how slow a backtracking engine can be. In 28 characters, you can get an execution time that will make your laptop spin forever. You simply just say A ? Followed by a bunch of A's, and you search for just the bunch of A's in the end. A backtracking engine is going to continue greedily matching those A's for days. You only have to get about to 28 characters, I find, 28 A's. Do that pattern. So what you're looking for when you're building this intuition is you want to minimize the amount of backtracking. That is where you could match, but it doesn't work out in the end. And you want to kind of keep those things to there. So let's use some more. Let's go back to my original example. How can I make Python perform better on this AB, AB, ABBB regular expression? Well, simple. Explicitly define where the matching actually splits. I know it seems simple, but when you extrapolate this to regular expressions you'd use in the real world, you actually find performance differences. While there is some optimization in Python against regular expressions and in other programming languages, going to the extent in PyPy it actually is interpreted to the bytecode and then compiled out from there. Same is true in C# and Java. What you end up, though, with is this is bubble sort versus quicksort. There's only so far you can go. The second example, which we can extrapolate that general rule from this first one, is when matching data structures. Directory structures. Here we see data, foo, and then same thing with bar, same thing with whatever. A better way to match that is to prefix it. Get your matching criteria all the way to the left where you can. Make sure that backtracking engine is processing the least amount of the string as possible. So now that we kind of focused on static strings, the more complex example and building the intuition here is really difficult. I've never mastered it, and I really know regular expressions. It's when you have examples like this, that in that first bad CSV match, the dot and the star, well, so the dot and the comma, they match the same character. They both match that dot. Well, that means that you're going to backtrack successful, unsuccessful matches. And worse for the NFA engines is that star is greedy. That means it must. You are demanding as the programmer that it match all the way to the end of the string. Then you backtrack to get that first comma, next dot, all the way to the end again, backtrack, get that next comma. That's how it works internally. I'm not joking. That's really how it is internally with Python. So a way to avoid that is to make sure that you have no overlap on your atoms. And here, in this example, I'm simply just saying, not comma. So that's simple. That'll give you 10, 100 times performance without even switching engines. So now I'm going to turn over to my colleague who's going to present a solution, a drop-in solution for Python that uses the Rust regular expression algorithm, and you can just use it, and it just works. And as I demonstrated, you get 10 to 100 times more performance, depending on how bad your regular expressions are. Because if you do use it, you no longer have to care about all these optimizations and this intuition I've tried to drill into your heads that is important and I think is underrepresented in programming documentation. So thank you. Here's David Blewett.
So I'm curious in the audience, who has heard what Rust is? Cool, good. So systems language intended to be a replacement for C. Doesn't have a built-in garbage collector, but you can use a garbage collector that's built into Rust. So if you wanted to be able to do something similar to Python and have a little bit more checking, you can do that. It has a system called crates to install packages installed by Cargo. So I've included some links here and also at the end of the presentation to be able to get a little bit of a feel for how Rust works. It's a little beyond the scope of the talk of how to really write a Rust program. But this is some good information. The playground is especially useful to be able to try out snippets and see the result immediately in your browser. So when we are looking for a replacement for Python's regular expression library, we wanted to be able to adapt, be able to call it from the Python interpreter. So the Ruhr package in the Rust ecosystem is exposing the regex crate to the C world. So if you have a C application, you can call directly into Rust's regex library. So in exchange for giving up some of the features that Andrew mentioned, back references and arbitrary lookaround, you get linear time searching across the entire string. So you can know that whatever string that you pass into the regular expression, you will have a very small amount of time to process it. So it includes most of the features that you would want to use, so capturing groups, lazy matching, extensive Unicode support, word boundaries. It's similar to Perl's matching semantics, so the leftmost match. The package that I wrote that allows you to use this from Python is called Ruhr-Python. What it is binding the C interface into Python's garbage collector. Sorry. So the interface is both Python 2 and Python 3 compatible. It's possible to build a binary wheel for the different architectures, so you can just install it without having to use Rust and do the compilation yourself. That being said, we have some issues being able to deploy some binaries, so if anybody is we would appreciate some help with some of that packaging for binary wheels. It gets kind of hairy. So the design decisions that went into this library were twofold. We wanted to make sure that from a low level, you could have as high a performance as possible through the Rust interface, but also be able to have it be a drop-in replacement for the standard library. So the standard library tries to make an object-oriented approach to using regular expressions, so it's relatively heavyweight. You have to compile the expression ahead of time. You get a match object back. The Ruhr Python package duplicates that API exactly, so you can just simply do import Ruhr as RE and do the exact same operations that you would need to do. We expose the constants that the standard library does, the same module level functions, the same objects that the match object, all of those interfaces are exactly the same as the standard library. The lower level expects UTF-8 encoded byte strings. So the choice before was that in the high level, as in Python 3, the default is Unicode strings. So as you're passing it both the expression and the data that you want to search on, it should be a Unicode string. And as you go down to the lower level, if you pass it a Unicode string, it will throw an exception saying that you need to pass me a byte string. The Ruhr interface allows you to only pay for what you need, the computation that you actually want. So if you just want to see if this expression matches, you can just say, does it match? If you want to be able to know exactly where in the string it matched, that requires more computation, so there's a different function for that. If you wanted to know what the capturing group, what we found in that string, that requires more, so it's another function to call. But in this way, if you have an extremely regular expression heavy application, you can only pay for what you need. A lot of the times, just a match is sufficient, and you can save a lot of computation overhead. So here's the links that I mentioned before. I published a binary wheel this morning, actually, for CPython 2.7. So it's published for OS 10. It should be available for the last 2 point releases of Sierra. That being said, we've got it hooked up to Travis that's building binary wheels for Linux, but we could use some help on being able to automate some of that. So if there's anybody in the room that has experience using Travis or other automated build systems, we would appreciate it. So most of the time, we consider Rust to be a black box. So one of the reasons I was excited about this is as a localized change of just swapping out the interface, it's a pretty easy way to get Rust in production without having to do a complete overhaul to use all of Rust. So that being said, there's not a whole lot in my code. Let me see. Let me pull it up real quick.
Are there other things in Rust besides Rust's Regex engine that you are interested in?
Sure. By the same author of the regex crate, there's another add-on called finite state transducers. It's a way of being, similar to Python's set semantics. Here. So here's the lowest level. We are using Python's CFFI package to expose the C API, so we get the. Sorry. So it gets a little bit hairy, so we have to make sure that we are attaching the garbage collection mechanisms from CFFI to clean up the Rust objects that we've created. To answer your question about the finite state transducers, it's similar to Python's set system of being able to have to do very fast lookups to see if a certain element is in that set. What it offers over Python is that it has a memory map interface. So you can, if you have a very large set of items that you would like to check, you can save that state to a file on disk, and it will only read the elements that you actually ask for out of that set. So here's the interface that I mentioned before, where you're asking for the very lowest level if it does match, or return me the start and end of where it did match, things like that. So here is the lowest level of being able to instantiate the C objects. It's kind of hairy from a Python perspective. The wrapper on top of it is slightly more Pythonic. So makes use of Python's drawing a blank.
Import this.
Yeah, as we read before, it's just a way of interacting with the code that it follows a certain set of semantics. So import this in a terminal will give you some of that.